Hello and welcome to Embedded. I'm Elecia White alongside Christopher White. We're going to be talking about C++ with Jason Turner of the CPP podcast.
Hi, Jason. Welcome to the show.
Hi, thank you for having me on.
Could you tell us a bit about yourself?
I am a C++ developer. I've been working with C++ since 1997 or something was the first time that I used it as a hobby language professionally for over 16 years now. And I am a trainer and, as you mentioned, host of CPPCast and host of C++ Weekly, which is my YouTube channel.
Okay. Now, I have a lot of questions about C++ because it's a language I've heard about for a long time.
Just a few decades.
Don't really use as much as I feel like I should. On the other hand, before we do that, I want to do lightning round where we ask you short questions and we want short answers. And if we're behaving ourselves, we won't ask why and how and all of the follow-up questions.
Okay.
Favorite C++ keyword?
Constexpr.
See, I knew that one. A tip you think everyone should know?
About life or about C++?
Whichever.
Whichever. Both.
Well, wait, this is supposed to be lightning round. I'm supposed to be answering these quickly, huh?
Bam, bam, bam.
I'll edit it so it seems quick in the end.
And he'll take that out, too.
Okay.
Maybe.
Maybe, yes, exactly. I'm sorry, I just have no idea.
Okay. Would you rather give a talk at a trade show style conference or an academic style conference?
I guess I've only ever done academic style conferences, so I have to answer that. Or maybe I could say trade show because I've never done it before.
Which is better, constructors or destructors?
Destructors.
Would you rather spend your next work day programming or giving class?
At the moment, programming, because I've been giving a lot of classes lately.
Which would you prefer to learn things with great breadth or depth?
Depth.
Okay.
Okay. Now on to the meatier questions. C++.
Okay.
Why use it?
Wow. Why?
Let's start with the big question.
Yeah, so it's an easy one. I can answer this in like 5 seconds, maybe. I would say main reason why is because C++ has been designed from originally with the principle of zero overhead abstractions. So anything that C++ has in the core language would not, the principle basically says it is not possible to implement it by hand any better than the thing that's built into the language. And that's something we can pretty much rely on. I've been trying to make a point of demonstrating that for a while now, past few years since I've been speaking at conferences and such. So if we know what the zero overhead abstractions are, we use them appropriately, we can get really high-level code that compiles to nearly nothing.
You use Matt Godbolt's compiler explorer quite a bit in your talks to show how you go from what looks like a completely foreign templated constexpr sort of line to 4 or 5 assembly lines. How did you find that? And how do you figure out how to make your C++ do that?
Matt's website, which is Compiler Explorer, godbolt.org, it was, I'm not sure when I first became aware of it, but I do remember the first time that I showed an example of the output in a conference talk, and everyone was basically like, whoa, how'd you get the assembly language output of what you just did there? And since then, I've used it. I can't even guess how many tens of thousands of lines of code I've written into a Compiler Explorer window just to explore what it's possible for the compiler to optimize and what the resulting code is. And it does take a little bit of practice to be aware of what things the compiler can optimize and what things it can't. And it definitely takes discipline to know when to use the right techniques and not just throw everything at the compiler all the time simply because you can. Because C++ is a multi-paradigm language with an awful lot that you can throw at the compiler for sure.
There really is an awful lot. I mean, I thought I spoke C++, and then I watched one of your presentations and realized that I spoke C with classes.
Yeah, maybe C++ from the 90s.
Yeah, C++ 98.
Well, even though I've been doing a lot of thinking about this lately, and C++ 11, 14, 17, they all enable higher level abstractions. Like, we got one of the main things that we got in C++ 11 is lambdas, and variadic templates are cool, but let's just go past that for the moment. And lambda is just a user-defined anonymous function, and the compiler treats it truly as that. It's just a function, but it's easy to declare it. And then in C++ 14, we got generic lambdas, so we can just say that the parameter types are auto, and that's a shortcut for making a template function. So it looks really clean and easy from the user's perspective, from the programmer's perspective, but it's something that the compiler can just do the optimal thing with as much as it wants to. And we can see, generally speaking, that lambdas are also something that's a zero-cost abstraction.
I think of lambdas as sort of inline functions that are passed by pointer sort of into another function. And in Python, I think of them as more generators, although I know Python does have more proper lambdas, but the generators are kind of what I understand. How far off am I?
So if you have a lambda that does not have any captures, so it knows nothing about the surrounding scope that it was created in, it is a function pointer. It's totally fair to think of it as a function pointer. If the lambda has a capture, so you're saying there's some variable in the local scope that I would like to either take a copy of or a reference to this local variable, then it has to become an object, something that can own that variable. And at that point, it's still something that is very efficiently managed because, well, C++ compilers have been very good at optimizing objects for at least the past 35 years or so. So it's just an object that you pass around that happens to have a couple of variables in it and the ability to call it like it's a function.
Okay. What is const expr? I mean, I have more questions on that, but really const expr, Chris explained it to me, and
I made up an explanation.
If you don't mind, I would like to take a quick step back, just on the topic of C++ being a large language.
Yes.
I've done this comparison recently, and if you look at the actual C++ core language spec, if you compare it to C, it's big. It's like 400 pages, something like that. If you compare it to Java's core language spec and C Sharp's core language spec, it's actually quite small. Like hundreds of pages smaller. I just thought I'd throw that out there. Now, it has nothing on Python, because Python's language spec is like 100 pages or something, and Ruby's language spec, or one of the two of them, I forget which one now, doesn't even seem to have an official language spec. They just kind of do whatever they want to in the language, so I'm not sure about that. But anyhow, I just wanted to make that aside. If
I think you were diving into some specific things, but I think from the point that both of us haven't used C++. I've used it more. I used it using with Qt maybe 8 years ago or so, or maybe 5-6 years ago, but not in recent memory. I guess from our perspective as embedded developers, we have the subset of C++ that we kind of understand: classes, private, public inheritance. Maybe not using multiple inheritance. Templates are a scary thing that we don't want to touch. Exceptions are a scary thing we don't want to touch, and that's pretty much the ball game. We don't use STL, or I guess that's been subsumed by something else. So I guess what's changed beyond kind of that core of the object-oriented structure, and what might be of use to people who are kind of wary of C++ as being bloated
or confusing,
or confusing.
See, I was just going to ask about each individual thing.
Well, I at
but
least
your
wanted to have that
question
header there before we did that.
is better because it's broader.
Okay, so in the broad scope, it's fair to say very little realistically has changed. We've just been given cleaner abstractions for how to talk about these things. I mean, you could implement your own class that had the call operator, the operator paren, overloaded in C++ 98. And that is effectively exactly what a lambda is doing for you. But the lambda gives you like a one-line way of doing this instead of like a 10-line way of doing it. And it's in the same scope. It's something that's highly optimizable by the compiler, and it knows exactly how to deal with these things. And we've gotten ranged for loops, which are a convenient way of looping over anything that's iteratable, and that includes C-style arrays and standard library containers, like you mentioned, the STL. But if you're not using those, that's fine. And all that does is compile directly into something that calls basically the begin and the end over the range of the for loop, or excuse me, over the elements in the container for you. And for a C-style array, that's the same thing. It gets a pointer to the beginning of the C-style array and a pointer to one past the end of it and loops in between that range and operates on it. So it's like, a one-line version of something that would have been 3 lines with the potential for bugs of accidentally having the wrong size of the array or iterating off the end of it if we were using some sort of a magic number marker or looking for a null terminator or something like that. But if we know the size of it at compile time, we can pass it to the array, to the ranged for loop, and the compiler can do something very good with it. In fact, ranged for loops in a way become something that some of us like to call a negative cost abstraction, because now the compiler knows the exact range of the loop at compile time, and it says, well, I know exactly 3 items are in this or whatever, and it can unroll those and do constant folding and make the whole loop just go away. Or if it's values that it knows at compile time, then the entire calculation or whatever you're doing goes away at compile time. So lambdas, ranged for loops. We'll get to const expert in a moment. I think we do need to talk about that. Templates have stayed the same for the most part. They've gotten a little bit more features to them. I wouldn't say they've necessarily gotten easier to use, but we do have variadic lambdas now, which is basically a way of saying, variadic templates. I got off track there somehow. It's basically saying we've got a function that can take any number of parameters. And now in C, you have variadic functions, but in C, you don't know at compile time really what the types of those arguments are. They're basically void pointers, and you have to do something with them correctly. And
so
C++...
like printf.
Sorry, go ahead.
That's
like printf.
Printf. I just want to make sure we have concrete examples for some of these things.
Yes, sorry, like printf. And now in C++11, we have a variadic template way of doing that. And we know at compile time exactly what types of parameters have been passed to our function. And the compiler can do all the compile time checks to know exactly that this thing is doing what we want it to be doing. Where with printf, in your example, it takes a whole set of extra compiler heuristics to know that it's supposed to be able to match up types that are in the constant character string with the things that were passed into it. And that's like compiler magic. That's not anything that's built into either the C or the C++ language spec.
That's been one of the interesting things about C++ is learning that you should trust the compiler even more. I mean, in C, we've been saying, at one time you could optimize your C, you could optimize your assembly to be better than your C, but now you should just be looking at your assembly, optimizing your C if you have to. You should definitely be writing in C because your compilers have gotten a lot better. And it sounds like in C++, they've gotten even better because so many people are working on it.
Oh, yeah. I mean, what optimizing compilers can do today, and to be totally fair, our C++ optimizing compilers are C optimizing compilers, right? It's the same back end for Clang, GCC, and Visual Studio. And we can pretty much rely on the optimizer to do the right thing. It's just in C++, because we have more type information knowable at compile time, the compiler has that much more to work with to make it possible to optimize it.
Okay.
So we're giving it more information and it's doing stuff with it.
Exactly. We're giving it more information and it's doing stuff with it. One example that I've been showing a lot to my students lately is you take a C-style array. Now, it's effectively impossible to pass a C-style array around, right? If you pass it to a function, it's a pointer. That's correct, right?
Yeah.
Okay. And so C++ has this thing that was added in C++ 11 called standard array, and it's really, really, really simple template class. All it is a class that contains a C-style array. But the type and size of this array is baked into the type information for standard array. Now, if I pass a standard array to a function, I'm not just passing a pointer. I'm passing a pointer or a reference to an object that knows how big it is. So every calling function knows I'm working on an array that is however many elements wide, and that gives the compiler that much more information to work with. So any for loop or anything, again, coming back to like a ranged for loop or something, anything that's going to iterate over that data knows the full size and type information at compile time and is able to, again, do more with it, more constant folding, loop unrolling, whatever it needs to do.
But does the memory get, is the memory static? Is it at compile time? Is it at runtime? Am I worried about, in embedded systems, it's like no dynamic memory. You have to have all static memory. It's just one of those rules that eventually we'll grow out of, but we haven't yet.
Speak for yourself.
No, sure.
Some of us have heaps.
We're talking about stuff that, like if I'm talking about a C++ standard array, the new container type added in C++ 11, it is something that lives on the stack. You know exactly where it is, and you can pass a pointer to it if you want to, or a reference. But when we're talking about the disassembly, a pointer and a reference are the same thing, to another function, and the function can operate on it. Or you can return them from functions, which returning a C-style array is effectively impossible as well, right? You can return it from a function, and with guaranteed return value optimization in C++ 17, you know for a fact that there will be no copy or movement of that data at all. So you don't have to do a heap allocation to create an array and return it like you might have to in C. You can create a C++ 11 standard array, return it from a function, and ultimately what the compiler does is construct that in place at the call site. So anything that would cost something goes away, guaranteed by the standard.
So if I had done an array, it would come off the stack as soon as I came back from the function. It would just be destroyed. And the only way that I could pass it back if I wasn't using a heap is if I made it a global variable or static.
Right.
But you're saying I can pass it back and it's on the stack and it doesn't go away. That seems
Correct.
magic.
Well, no, it's not. Because if you returned a structure from a C-style array, a structure from a function in C, then you would get data returned back, right? It's not going to automatically become a pointer. It's just this ugliness that exists in the old array. I say as a C++ developer, the old array style. and C-style arrays, that they just decay to pointers. There's like no way around it. But in C++ or in C even, if you return a structure from a function, that's a thing, right? It's an object. It's not a pointer. I guess I don't know what the correct term is to use in C for what a structure returned from a function is actually doing.
Block of memory.
A copy.
It's a block of memory. It's copied, yeah. And in C++ 17, it's guaranteed to not be a copy. It's like the compiler. So if I call a function that is returning a data structure in C++, specifically in C++ 17, although compilers really have been doing this as far as I can trace back since 1996, I have not found a compiler that would not do this for C++. If you say, I have a structure, so like my struct, whatever it is, equals some function call, and that function returns that structure back to you, the compiler allocates on the stack where the memory needs to be in the resulting place for the caller, and then it passes forward to the function that it's calling, a pointer to that memory location and says, when you fill in that data structure, fill it in back here where the calling actually took place. So returning, for example, a data structure from a function in C++ is effectively, and I'm exaggerating a slight bit, or I'm simplifying a slight bit, has basically been free for at least the past 33 years. Never been a copy.
Okay.
There are caveats.
Yeah, there always are.
Of course. But so that's just one thing that I like to point out to my students when I'm showing them where C++ can be efficient. I think those are the main things really that we've gotten in the last, say, 7 years from the language, though I'm sure I'm missing something. Well, const expr, we still haven't talked about that.
We'll get back to it.
Okay.
How do I learn C++? And what do I learn if I say I want to learn C++? Do I go for 11? Do I go for 17? Do I just try to refresh for 98? What do I do and how?
Well, okay, from the perspective of your listeners, I believe, since we're talking about an embedded world here, one of the problems that we have is embedded processor manufacturers not supporting C++ very well.
Yes.
So, I mean, the compilers are there, right? 90% of the chips out there, at least, I'm sure, have official support from Clang or GCC, right? I assume are the main compilers you all are using, except for the rare, the ones that were vendor specific. Is that correct?
Mostly, yeah. I mean, I think the vast majority of the common chips are GCC-able.
Yeah.
Okay.
A lot of people are using other compilers, IAR and Kyle, to name two. But all of the ARM chips now can be supported with GCC, and free versus pay for. A lot of people are going for free, even though the pay for sometimes is a better format, although often isn't. So, ARM, I've played a tiny bit with AVR and MSP 430 chips, which both have support from Clang and GCC as well. And we're talking, those are teeny tiny chips, right? Well, I don't know how much capability you can get in an AVR these days, but it's an 8-bit processor, right? Yeah. Let's just go with 8-bit processor and laugh and walk away.
8-bit processor, yeah. So AVR has full complete C++ support from GCC and Clang. But if you're using an ARM chip or something that's a little bit more complex, that maybe has multiple cores or multiple CPUs in it or something, getting a good support from your compiler vendor, from your CPU vendor is going to be a little bit harder. Apparently, like I just saw a talk from Michael Case on this at C++ Now, which was a conference a couple weeks ago, where he was pointing out that basically it comes down to the linker script not being complete. Like that was the main thing that he found. Otherwise, the tooling is there. And the linker script becomes a bit of a problem for C++ if you want to support things like exceptions, because the compiler needs to know where to put these things in memory. But if you're not worrying about exceptions and you're just using the regular language features and you have a compiler that can support it, then I would say just learn C++ 17. I would not go before C++ 14. I personally consider C++ 14 to kind of be a bug fix to C++ 11. It has just a few minor tweaks that are really important for really being able to make the most out of the newer abstractions. But otherwise, I would say try to forget what you think you know from C++ and try really, really hard to not think of C++ as C with extras. Think of C++ as a completely different language. If you go into it that mindset, I am learning a different language, then you will hopefully have a little bit more success with not trying to apply what you know from C and think, oh, this is the efficient way to do it, because that's not true in C++. And I've had this experience with teaching students. I've had to be like, they'd be like, whoa, but it's more efficient to call malloc and return a pointer to the thing. And I'm like, no, it really, really isn't, I promise you. And I'll bring it up in the compiler explorer and I'll show them the differences and be like, look, you had to do a heap allocation here. And in C++, all the code that we just wrote completely went away. So, just trying to break that mindset. It's not C with extras. It is a different programming language is, I think, good.
That's one of the things that an embedded developer might take issue with, some of the hidden nature of what's happening with memory, because a lot of the time we're doing things as explicitly as possible because we have very limited memory available.
Right.
And it's in various segments that might be well-defined in various sizes. So if we know we're, basically getting things statically 90% of the time, maybe we have a small heap, but we're very careful about using that. Is there the worry that comes up in my mind is, okay, well, C++ is doing these things very efficiently, but I don't know where it's doing these things. And I don't know at any given moment necessarily how much is taken for certain operations. Does that make sense as a worry? I know it may not be valid, but...
I know, it makes sense. And so a talk I gave a couple of years ago, which was writing a simple Pong game for the Commodore 64 in C++ 17.
Okay.
The talk had a few hundred lines of code to it. And I walked the audience through, like, okay, I'm going to do this thing, I'm going to do this thing, and I'm going to add some lambdas here and whatever. And with each step, I had the compiler explorer up, and I was showing what it compiled to. And one of the comments I got from this was, I never knew it was possible to make assembly language so interesting. But I did this for 90 minutes 70 minutes on stage. And the kind of behind the scenes bit of this story is it did take, it was very carefully crafted code to know exactly what the compiler was going to generate. And part of that was because I was writing code for the 6502, MOS 6502 CPU ultimately, which is very old now. And there's no compiler for the 6502. So I was actually having to transcode it from x86 assembly to 6502 assembly. So I wasn't even necessarily exactly concerned about how much memory was used or where things lived on the stack or whatever. I also had to be specifically concerned about each type of x86 instruction that was even being generated to make sure it was one that I could translate later in my post-processor. And basically, the way it worked when I was doing that, preparing for that talk, is I did the entire thing in the compiler explorer, and I got to become comfortable with what the compiler was able to optimize. And now, today, 2 years later, if I'm unsure about what something's going to do, I throw it in the compiler explorer, I run through it, and I go, oh, okay, right. I can trust the compiler's able to optimize this, and now I'm going to move on with my life. And, with a little bit of experience, now I know what's going to happen. But for the most part, the compiler's never going to dynamically allocate memory for you. That's just simply not going to happen. So if you learn where it is always going to optimize things like return values from functions, return value optimization, then you learn to trust those. And if you learn what kind of algorithmic things it can do, for example, templates, a template in C++ is never less efficient than writing the same code by hand. It's impossible for it to be less efficient because all the compiler did was swap out the types that you passed into it with the types that should have been there. So you put in type name placeholders, it swaps them out with the actual types that were used at compile time. So you can, call the same function 4 different ways with 4 different types, and it will always generate the most efficient version of that function possible. And then it would likely, not always, but it has the ability to then inline those functions, which will, make the code that much more efficient if it can.
But it will make the code larger.
No larger than if you had written, if I make a template that takes one type, has a simple templated type in it, and I call it with 4 different types, it will be no larger than if I had written 4 different versions of that same function, and oftentimes smaller than if I had written 4 different versions of the same function.
Right, because I have a code that I work on, and I have several different versions of, say, a matrix mult, and one's fixed point, one's floating point, or things like that. And that's not a great example because we have to do different things in there, but yeah, there's two different copies, and even if you have the same exact operation, you're going to end up with 2 different copies in C, just because if you're multiplying ints or floats, right?
Right. Yeah.
And you're saying that won't happen with templates if done correctly.
Well, I'm saying if I needed, if I write a template function, one time I call it with ints and one time I call it with floats, the compiler will generate for me 2 different versions.
Got it. Okay. Yeah.
And it's sometimes possible that it will actually result in a smaller binary than 2 different versions, but assume it just made those 2 different versions for you. Exactly. So the only time template bloat comes in is if you are reckless with that and you create templates and call them with 10,000 different types because you can. Because in C++, generating new types at compile time is not hard.
Okay. So that all makes sense. And I actually know that C++, so many of the features are scrutinized because everybody says bloat or slower or bigger or something. And so just about every feature I can ask you about, you will be able to tell me is just as good as if you did it in C, because that has been the drive for 35 years.
Right. And I'm coming from an unfair standpoint because I teach people all the time that it's that. Yeah.
But let
me ask a question while you're thinking about this. I think one angle that people might challenge some of this is saying, well, in C, most things are kind of explicit, right? You do something and you kind of know what's happening. That's not really true because there's all sorts of examples where operator precedence and sign promotion or type promotion are all screwy.
And then by the time the optimizer gets its hand on it, and then the CPU executes the instructions out of order and everything else, you have no idea what happened, really.
Right.
But you feel like you did.
But with C++,
you feel like you did, yeah.
Now we have all these features, and some of them do very implicit things. Like you mentioned, if you have a template and then you kind of carelessly call it with a bunch of different types, that's going to explode your code. But you might not make that connection if you're not a very sophisticated developer or have sort of knowledge of how templates work under the hood.
Right. Now, I accept that argument, but I would say this. I think the likelihood of accidentally calling a templated function with a bunch of different types is low. Just like the likelihood of accidentally calling, well, I don't know. I mean, if you had a function in C, you have one version that takes an int, one version that takes a float. Now you call it with a double, you call it with a short, you call it with a long. The compiler's going to do implicit, well, implicit
you name them all
differently.
You name them all differently. You don't do anything implicit there. If you call it with a double, you're calling matrix multiply underscore float.
Yes, that's my point, though. You're calling matrix underscore multiply, float, but you're calling it with a double. That's what I'm trying to get at. And now you've just done a truncation, right? And that's allowed in C, right?
Yes.
And now is the compiler warn you?
Well, usually it'll warn double to float.
Okay, it would warn double to float.
Truncations are usually warned. But Christopher's question went back to my hesitation, and that is, you can do things in C very explicitly. And the way I do them, and the way Christopher does them, and the way other people do them, they may be stylistically different, but on the whole, they're not that different. But when I look at C++ code, it feels almost artisanal, that it is an expression of whoever wrote it and how they feel about templates and STL and classes, and it's about them as much as the problem they're trying to solve. Is that just because I'm on the outside, or is there some truth to that?
There's probably some truth to that. Yeah.
That doesn't seem good. I want science. I want one way to do it. I don't want...
Wait. You're telling me that doesn't happen with C code?
It totally does.
There's very readable C code and very not readable C code
And we can have a war about where the curly braces go and how many spaces are in a tab and whether you should have Hungarian notation or if every variable should be named
or
I.
if there's one
I'm pretty sure we've all agreed that I'm sorry, go ahead. What was it?
But yeah, there's tons of stylistic things that happen.
But in C++, in C, once you get rid of all of the top surface level, then you're left with 5 different algorithmic ways to do it. And I feel like in C++, you're left with 500 algorithmic ways to do it. And because of that, I feel like I'm not learning it right. I feel like I can't win. I can't learn it well enough to be confident.
So you feel like you can be a doctrinaire C person easily, but you have to be a cafeteria Catholic with C++. Terrible analogy.
I have no idea what that meant.
But you can. There's more to pick and choose from and leave aside. So you can go whole hog into C++ if you want, and that's a different style than say using 3/4 of it. And maybe it's not great to use 3/4 of it.
So I personally, this comes up all the time. You know, people say C++ is bloated. They should break compatibility with the past, basically. As a teacher and as a programmer, there is very few things I would remove from the language because they all have most of them have real legitimate uses. And it does take, discipline to know when to use them, but it's no different than any other language. I don't think. In C, if you see code that is calling malloc everywhere and never uses the stack, you're going to think this is bad code, right?
Yeah.
I hope.
Yeah.
If you see code that is constantly I don't know, I can't think of anything else that's great right now without repeating myself, but just consider if you had, most of us these days are polyglots. We know something about other languages. If you could have the expressiveness of Ruby and some trust that you're getting the efficiency of C, or better in some cases, then does that seem worth learning the extra features?
Yeah, definitely.
As long as I could find a way to learn those extra features in a way that I could use them. And in C++, right. I can learn about lambda functions, and I can learn about templates, and even STL, which I do want to get to, and the standard library stuff. But when I read other people's code, I look at one person's code, and it's this way, and I look at another person's code that's doing essentially the same thing, and it's that way. And I don't know what I want my code to look like because I'm too much of a newbie. There's no classical C++ that I am aware of. Although, as I was preparing for this, I realized you have a GitHub that's about this, don't you?
I have a GitHub. Let's see. I have the CPP starter project.
The best practices manual.
Oh, I have that as well. Yes. The best practices manual is not everything that I teach for sure, but it's cppbestpractices.com, and it's mostly about, basically keeping things clean and simple.
It did have some nice references to other tools and looking at how you put things together. I guess if I'd had that earlier, maybe I wouldn't feel so leery about some of the new features. Because I really have gone through this process where I read a book and then I'm totally daunted by all the things I'm learning, and then I go read some stuff and it's all different.
And it's true. And we have a problem.
But is that specific to C++? I don't think it is.
It goes back to the artisanal code.
I've seen Python
comment.
That's confusing it's confusingly different. Like,
like 2.6 versus 3.
I've seen Perl that is confusing.
Or, I mean, I've seen people have arguments in code reviews on Python where it's like, oh, you're not using this language feature. Why are you doing it this way? Like, oh, because it's much easier for people who come from C and don't know Python well. And it's like, what?
It's not the Pythonic way to do it.
Exactly. Yeah.
I totally agree with you, and it is a problem that we have. Like, if you look at Stack Overflow, for example, and it's probably true of any language, but I know it's really true in C++ land, that like the early answers that get upvoted and get the most links from Google are the things that come up in a search, and they're not always the right thing or the good thing to do.
And there is difference between C++ 98 and C++ 17. And the difference is daunting enough that if I know one better than the other and a teammate is the other way, our code is not going to look similar. It's going to be confusing for the third person who comes in and knows C++ 14.
That's when you hire a competent trainer to come in and get you all on the same page.
What is it you do during your day job, Jason?
I occasionally teach people at companies how to write good, clean, modern C++.
Let's see. I have some listener questions I want to go through, if that's okay with you.
Sure.
Can you elaborate on the usage of pass by reference versus pass by value? Some people say pass by value is always faster, but the listener has read that in certain cases, pass by value, a copy, can be faster depending on the type. We've covered this a little bit, but maybe the direct question is cool.
Sure. So it depends an awful lot on the CPU architecture that you're programming for. If you're talking AMD 64 or 64-bit Intel compatible stuff these days, and the 64-bit C++ ABI, if the things that you're passing can fit in 64 bits or less, then passing by value is almost always more efficient because the compiler will simply shove that into a register. And if you're passing by reference, then it's going to have to do a memory and direction to actually access the data of the thing that you passed in.
And note that you said 64 bits, but if you're on a 32-bit processor, then it's 32 bits. If you're on an 8-bit processor, it's 8 bits.
On a 32-bit Intel architecture, it's going on the stack regardless. It's not going to go into that highly efficient register parameter. That's
we don't
the
care about
difference.
Intel. It's all about ARM.
I don't, let's see.
I'm not sure the answer there either, honestly.
I'm
pretty sure. I mean, we can go to godbolt.org and try it out. But your answer, I agree with the caveat that it depends on how big your processor is.
Yeah. And I actually, if I might plug my C++ YouTube channel, I have an episode coming up. I haven't actually even edited it yet. So you have to subscribe now. And like 2 months probably, that is comparing these different things and what the compiler can do with packing data into registers when passing to function parameters.
And this is C++ Weekly, where you look at a screen and you talk and you look at the assembly, and it's all pretty self-contained.
Pretty much. Each episode is pretty much self-contained. I have a few multi-parters, but they're somewhere between 5 and 10 minutes each, and it's just a thing that I want to talk about. Sometimes people will like comment like, oh, you're teaching bad practice here or whatever, and I'm like, I'm not necessarily teaching anything. I'm just talking about the thing that I felt like talking about that week. So, don't take everything that's on that channel as like, Jason taught this is the best practice thing to do here. No, it's just an interesting thing to talk about.
Okay, next listener question from a listener who's a fan of C++ for embedded, but mostly in the C with classes camp. And he avoids templates because they generate lots of code, which we kind of talked about. That's your fault. And it's sometimes painful to debug, which means that he's closest to C++ 98. He admits to improvements with the null pointer and shared pointer types and better initialization. But what new features in C++ 11 or 17 or 14 do you think most apply to the constrained environment of embedded development? And I want to add a caveat to that. What features do you think we should be avoiding as well as applying?
Well, in a constrained environment, I avoid all dynamic allocations.
Yes.
Personally, exceptions, totally agree. Like some CPUs, it's impossible to support exceptions, but that's not new, right?
Yeah, we've been avoiding exceptions for a long time.
Right.
I've avoided them on processors that could support them. So.
Yeah, and the community as a whole is largely avoiding exceptions altogether at this point, because there are better ways in many cases for how to handle errors. But yeah, we touched on the bloat or not from templates, null pointer. So I would say most of what's been added is things that have made it better, even from an embedded standpoint. And I would say definitely you should be looking at the algorithms, because all but 3 of the algorithms can be implemented in a zero-cost way. And those are stable sort, stable partition, and oh no, I always forget the third one. Well, anyhow.
A third one.
And what's that?
A third one.
A third one, yes. And lambdas, basically. So if you're doing any kind of data processing at all, you should be looking at algorithms and lambdas and using them in your C++ 11 forward code. And they will, I can just about guarantee will make your code both your actual code that you programmed shorter and more efficient.
Well, this goes to one of the things that we commonly complain about as embedded developers is, I'm starting a new project. I'd better rewrite linked list and circular buffer and queue and things. And those are all container classes that exist.
And yeah, it kills me that we aren't doing that. And there are search and sort algorithms. You don't have to look up a bubble sort on Stack Overflow and copy it into your code anymore.
Get it on Wikipedia.
If you use, standard vector can actually be super efficient as well. I mean, if you're using it, in a constrained context, it will do exactly one allocation and exactly one deallocation, exactly like you would expect a hand-rolled thing to do in C, but you didn't have to write it yourself.
And the strings library, I am not the only person who has had bugs in their string handling system. I'm just not.
But these are things take size. These are libraries that, I don't know how you'd say, I don't want that, right? If it's part of the language.
Well, so they're all
link time optimization.
Sure.
Well, and basically all of the standard library things are templates. They don't do anything to your compiled code unless you use them. Because a template effectively doesn't exist.
Right, okay.
An instantiation of a template exists. So I can include the vector header and I can link against the C++ runtime and not see vector anywhere in the resulting binary. Now, if I actually create a vector of integers, then I'll see the code that was around it get inlined into my code, basically.
Okay. Well, that's one of those implicit things then that you might get excited and say, well, I'm gonna grab this string. I'm going to do all the string manipulation using the standard stuff, but it's too big to fit on my 8-bit AVR with 32K and fit my program. I mean, those are real concerns.
Yeah, kinda.
Okay.
I mean, I can show you examples where I create strings and run algorithms on them, and depending on what's known at compile time, the resulting binary is just like return 5.
Right.
Like, because they are all templates, the compiler has complete visibility into what those things are doing, and it can do very efficient things with them at compile time if it has enough information to.
And I mean, we think about algorithms, and some of these are big and interesting. I mean, I've written I to A too many times, and to find it in the algorithm is just really nice, even though it's going to be a little bigger because I don't need everything, but I don't care. That's worth a few extra bytes. Yeah. But max, I mean, usually we pound to find max, and it's, and then you have to have the right number of parens, and you have to think about what if there's a plus when it gets passed in.
Oh, yeah, it's almost impossible to get right as a macro, yeah.
But here, I mean, there's a function that's part of the language. It's compiler developers have thought about all these things you're going to write bugs about, or I'm going to write bugs about.
And I guess as a rejoinder to my own complaint is if you're working on a tiny system, you're always aware of, you have to always be aware of the implications of what you're using. And that doesn't change whether you're doing C or C++. You
used AVR, but AVR is Arduino, and Arduino is C++. Mm-hmm. It's not the best of C++, but they do templates and classes and multiple inheritance. I don't think it's...
But they're not necessarily trying to fit that alongside a Bluetooth stack. From a product development standpoint.
Well, yes. Okay. Now we can't talk about Arduino.
That's why. Great. You can do whatever you want when you've got Arduino, and you throw your hands up and cry when it doesn't fit. But somebody hands you a processor and says, "Okay, this is what it has to do, and we have these libraries we're bringing in. You have 5K." Mm-hmm. Now you have to make some choices and be aware of the implications of the things that you pull in. That's.
But Jason is saying you don't pull in anything you don't need.
Right, and that would be. Yeah. And I'm saying that would be true of anything you're doing.
I would like to say, though, before you get too excited about A to I or I to A, or those functions, those actually come from the C standard library, don't they?
I think so.
No, I think I was out of there at that point. Let me see. Maybe
regardless, they do. A lot of those functions that are around that area rely on the currently set locale, which is its own can of worms.
Let's not go there.
Yeah. Okay, so there are things. So I'm looking at this C++ reference page, and there's algorithms library, an iterators library, numerics library, and then down here with a line separating it, there's standard library extensions.
Okay.
Where is STL? I remember STL. STL was okay. It was a little complicated.
It got absorbed.
Is it in the iterators and algorithms part, or is it in the standard library extensions part?
Okay, which page are you looking at?
Oh, I'm sorry, cppreference.com.
Okay, just making sure. Okay, so the STL, the standard template library, has kind of always been a colloquial thing. Like, as far as I know, the standard never actually called it that.
No.
It is the thing that is the containers and the algorithms, basically, with the concept of you have a container that's got begin and end iterators, and you can pass these iterators into your algorithms. Basically, that's what we think of as the standard template library.
There were a bunch of functions too, weren't there?
I don't know if we would have ever called them the standard as part of the STL or not. I don't know.
And anyway, STL doesn't really exist anymore. It's part of the language.
Oh, yeah. It's been part of the language since C++ 98.
Wow.
I am so old.
But I'm pretty sure I used the STL namespace like 10 years ago.
Well, there was Boost.
I've never...
I used Boost, which was sort of STL.
I didn't use Boost.
Anyway.
I've never seen the STL namespace. I've seen STD.
Yes.
Oh, maybe that's what I'm thinking of. Wow. Well, it's been a while.
Perhaps. I would like to comment on the topic of templates, and before we run out of time, there's a developer who's been doing a lot of conference speaking lately. His name is Odin Holmes, and he is Odin the Nerd, if you want to look him up on Twitter or anything like that. He is big in the embedded space, and he is a C++ developer. And one of the things that his library does is from using templates is he can say, like, I've got my embedded device and I need to set these 7 bits on an 8-bit register. And, he just writes very clean looking code that says, I'm setting bit 2, I'm setting bit 5, I'm setting bit 1, I'm setting bit 4, whatever. And his library is able to take that, say, well, you set 7 out of 8 bits, so I have to read that register, update those 7 bits, and write it back. Or if he wrote all 8 of the bits, it can, at compile time, say, I know that you wrote all 8 of the bits. There's no reason for me to execute the read. I'll do a single 8-bit write. And he has shown in his own code, considerable, 30% compile size savings in some of his embedded work. If I'm getting that number right, he could correct me. I think it's on the order of, it's considerable by taking advantage of techniques like that, taking advantage of templates to calculate at compile time the things that they needed to know.
Okay, let's go back to listener questions. This is a bit tough. One listener in the avionics community mentions the need for certification, and FAA, FDA for medical, highly critical applications like space. What parts of C++ have been okayed for that use? Much of the standard library, as far as I know, and as far as this listener knew, hasn't passed any certification for the highly critical applications.
Yeah, and I have, honestly, it's not something I can speak to. Okay. I know I've heard that, like, exceptions aren't allowed to be used, for example, but outside of that, I don't really know.
Oh, and I mean, there are small pieces of guidance. FAA has guidance on object-oriented practices and multiple inheritance. Basically, they say no unless it's for the interface.
Yeah, that doesn't make any sense to me because...
the rules for that are you don't want code you're not using. Every line of code, every function needs to be traceable to requirement. So if you have a multiple inheritance case where you have some code off that isn't currently being called or that may not be called, you don't want it in your code because you can't trace the requirement to anything. Multiple inheritance adds a layer of indirection that makes it difficult to do the direct trace.
It doesn't have to, though. I mean, you can do multiple inheritance without using virtual functions and just inherit multiple behaviors, and then you know exactly what's happening.
Yes. And I'm sure that somebody could make that argument.
I mean, I do know that the development for like the F-35 fighter jet, a great deal of it was C++. So I think they even have a published best practices thing. So people are using it. I don't know what you have to do to get it certified, but it's not impossible.
Okay.
Constexpr.
Should
we talk about Constexpr? We have more questions.
I would love to talk about Constexpr.
Let's go with Constexpr. I have one more listener question I want to get to, but let's go with Constexpr. What is Constexpr other than something really fun to say? Constexpr.
Constexpr is a portmanteau. Can I get that? Can I say that right?
Yeah.
Close enough.
It is a constant expression.
Okay.
And what you are telling the compiler is it is possible to do this thing at compile time. That's all you're saying. Now, if you have enough things that can be done at compile time, and you want to call some of them in a compile time context, I could say, constexpr int I equals call some function. And some function has to be constexpr. That function itself has to be marked constexpr. Unfortunately, we can't define that. But we're telling the compiler, I want to do this thing at compile time, and I'm calling a function that I already told you ahead of time can be done at compile time. Then the compiler does it at compile time.
Are these macros?
No. This is like, say you want a table of values. And usually we go to Excel and we generate the table, or we write a separate C program that generates a header file and that runs a function and generates your table. This is saying, just put that in your code and the compiler will do that for you and then turn it into a constant.
So your constexpr would be like, for all of the values from for 0 to 360 and 1 degree things, do sin x and put that in this array?
I think so. Do I have that right?
That is 100% correct, except for the fact that we don't have a sine function that is constexpr.
Well, fine.
But we're getting there. That should be in C++20, I think. Or you could write your own sine function.
Yeah.
Let's just say you wrote your own.
And that's not hard. I mean, writing... Oh, wait a minute.
You might have tables of tables or constexpr. It's constexpr all the way down.
It's constexpr all the way. So for the example of a table... a project that I was just recently working on was I was writing my own ARM emulator because I thought this would be something interesting to do. And I started realizing as I'm typing this, like part of my goal is to apply as many of the best practices that I teach to a brand new project. And I'm like, well, this could be constexpr, and this could be constexpr, and this could be constexpr. And then I realized that the whole thing could be constexpr. But a part of it was the the opcode decoding, I needed a table to say like, well, what kind of opcode is this? And I needed that table to be sorted because I needed the like most specific version to be checked first. And realized, well, there's no reason why I can't just write this table sorting in a context per context as well. So I have all generated for me at compile time, the opcode decoding logic that's stored in a table that's generated at compile time in the sorted order at compile time that I need to decode the opcodes for my instructions in my ARM emulator. And the end result is that I have an ARM emulator that I can, if I really want to, pass it a string of bytes at compile time and have it tell me what the resulting registers and memory layout would be at compile time.
Which I couldn't do in my Excel version, which I could do up to that point.
Right.
I mean, there is some temptation. I end up making a fair number of tables, fonts.
Command
tables. And
state machines.
Yeah. And doing them in Excel or handwriting them in code, it's not that big a deal.
Mm-hmm. But then you have a synchronization issue, right?
And a maintenance issue.
Yeah.
Yeah. I used to use awk for synchronization. Awk.
I've never done that before.
Let's not talk about that.
Awk 2020 is going to have a lot of cool features.
That's awesome. So, that's basically what context per is. You can just saying, I want to do this thing at compile time.
Which I guess has a lot of advantages, although they're not apparent. I mean, you have to think about what you're doing.
Well, to me, it's like there's a bunch of times when I've tried to do things like that in C to have it say, what are you doing? I can't evaluate this. So I can think of a lot of places where, just it seems like something you can do. You find out you can't, and you learn where you can't use it, and now you can.
Yeah, I mean, there's definitely still limitations. You can't throw exceptions, which is fine because you didn't want to be throwing exceptions anyhow, right? And you can't do dynamic allocation, but you didn't want to be doing dynamic allocation anyhow. I would say the main actual downside to it is that because the compiler has to know the definition at compile time, the definition effectively has to live in your header file. Otherwise, there's no way for the compiler to see the definition of it.
Yeah. Okay. Before we close the show, tell me about CPPCast. It's interviews, and you talk to interesting people, but I've always thought embedded was pretty niche.
Both, all three.
But a C++ podcast, that seems even more so. How do you keep it going? What's it like? Why do you do it? How much new is happening in C++? All the questions. Tell me about it.
Goodness. Okay. So we've been doing it for about 3 years now. We have over 120 episodes. No, it's more than that. Sorry. Whatever it is. We've been doing it for over 3 years now. We have a guest virtually every week. Sometimes it doesn't work out and we end up just doing a news-based episode, but there is constant news to talk about. The numbers that I'm aware of say that there's about 4.5 million C++ developers around the world right now. We've got something like 6 active conferences and new ones being formed regularly. So there's always something to talk about from the latest standards meeting or the last conference that happened, people that are speaking at the conferences, or what people are discussing as the latest best practices, that kind of thing. And occasionally we get the controversial thing on, or get someone from a different programming language, or talk about embedded, or whatever. But yeah, it's not terribly hard finding guests, really. There's a lot of people that want to talk about their personal projects or their talks or their research or whatever.
Cool.
Did I answer all those questions?
I think so, yes.
I try to.
I'm going back to, there are multiple C++ academic conferences. Are there any embedded academic conferences?
I don't think there's any academic embedded.
Yeah, maybe that's it. Or it'd be robotics, or it would be a sub-application field.
Now I feel like I feel bad, like I should revisit this and make sure I understood what you meant by academic conference. I mean, it's people just talking about ideas, and it's not sponsored by any particular company. Is that an academic conference?
Yeah,
Are they mostly professors?
Are they presenting papers and stuff?
Not in the same way. No, it's not like. I don't know. I guess it's called we say that we're submitting papers to the conference, but it really doesn't. It's not like a published paper kind of thing.
It's pretty
like, well, this
academic-ish.
is the thing that I'm talking about. It. Okay.
It's more academic than the embedded ones are. I mean, lately
not a trade show.
Our better conferences have been through like Hackaday and places that are less sponsored. We'll see. Maybe it'll get better.
I could say it's definitely not a trade show. I don't think, but it seems like it's somewhere in between those two worlds, maybe a little bit.
Well, I'm currently trying to figure out if I can really convince people who are having a conference about jellyfish to let me go, which is an academic conference about jellyfish.
Wow.
So that will be, completely pointless.
Let you go and speak, or just let you go?
Oh, just let me go.
Okay.
Maybe I could just wear a jellyfish hat. Okay. For people who are inspired to learn more about C++ and how to use it in embedded systems, what would you recommend? I know you teach classes, but do you have books you recommend or sites that people can learn more about the latest in C++ and how it doesn't suck for embedded?
Okay, so specifically about embedded, I guess I would...
about new C++.
At this point, there's thousands of hours of conference talks online.
Yeah.
Like literally
Too
thousands
many.
of hours of, yes. But you go and look at the top rated talks from CPPCon, and you will find a lot of good talks. So I mentioned Odin Holmes. He's doing a lot of talking about embedded. Michael Case is also an embedded developer. I mentioned him earlier. You could look up talks from either of those people and see what they are talking about. Odin's tweets a lot. And then there's, a new Twitter and conference that are starting to... Yeah, so there's two conferences around in the C++ embedded space. One is called Embo++, and it is held in Germany every year. That's Odin's conference. And then there's one called Meeting Embedded that will be getting started for the first time this year in Berlin, and that is Jens Veller. And you can follow Meeting C++ or Meeting Embedded on Twitter or find their websites also. I think those would be good places to start.
Okay. And I read Bruce Eccles' Thinking in C++, which opened my eyes to a lot of things. And I know you use Matt Godbolt's Compiler Explorer because it really does show you what's happening, and that is weirdly persuasive.
It is, yes.
Sorry, go ahead.
Well, I was going to take the bold stance of recommending my own CPPCon talk from 2 years ago on Rich Code for Tiny Machines was the name of it, where the one that I mentioned already, that I demonstrate writing a Commodore 64 game. And, it's an exercise in what's possible and just how much optimization the compiler is capable of doing.
And how helpless you become when you lose your keyboard keys. It was a fun talk. I do recommend it.
My laptop had crashed right at the beginning of that one, too, so it was exciting.
You handled it with aplomb.
Thank you.
Jason, do you have any thoughts you'd like to leave us with?
I don't know. Never stop learning, I guess. That sounds like a good one. I can make up some random something.
I think it must be time for Jason to go eat.
I've already had dinner, actually, but thank you for the concern.
Our guest has been Jason Turner, host of the CPPCast and independent developer and trainer. You can reach him at Empty Crate or find him on Twitter. Of course, we'll have links in the show notes. Thank you for being with us, Jason.
Thank you for having me on.
Thank you also to Christopher for producing and co-hosting. Thank you for listening. Thank you to Matt Godbolt for the introduction. Thank you to Joel Sherrill and other listeners who contributed questions. If you'd like to know who the next guest is and get your question in, well, you have to join the Embedded FM Slack channel. And to join the Embedded FM Slack channel, you have to kick in $1 a month on Patreon for at least 1 month. It doesn't come out to much, does it?
It comes out to $1.
We don't have ads, and we do greatly appreciate your support. On the other hand, if you just want to say hello, you can contact us at show@embedded.fm. Hit the contact link on embedded.fm. So now I have a question. I have a quote to leave you with. This one from Bjarne Stroustrup.
Nope. Mm-hmm.
Bjarne Stroustrup.
Nope.
Bjarne Stroustrup.
Bjarne Stroustrup.
Bjarne Stroustrup. This one from Bjarne Stroustrup. He's not going to cut those, is he? Embedded is an independently produced radio show that focuses on the many aspects of engineering. It is a production of Logical Elegance, an embedded software consulting company in California. If there are advertisements in the show, we did not put them there and do not receive money from them. At this time, our sponsors are Logical Elegance and listeners like you.